All right, how we doing? Doing good?
How you doing?
Doing good? All right, yeah. So today we will be wrapping up the final part. We're going to be talking about Laplace transforms and how to do them and what are we supposed to prepare for this exam. So I guess everyone finally gets the gist of it, but if you wanted to pass this class, oh, that's a funny looking L. Laplace transform of f of t, right? Remember that? Is equal to, we analyze the entire signal f of t from t, or t is equal to minus infinity to t is equal to positive infinity. We're looking at the entire signal f of t, right? Makes sense. F of t, we're looking at the entire f of t, e to the minus st, right? dt. Remember that? You memorize this and you're set and you're golden for this entire class. Does that make sense? Here you go. Here's your holy answer. Doom. We're done. Lecture's over. Just kidding. Nah. So if you've already reviewed the first and second Laplace videos I posted out, the first video was regarding just general Laplace transforms and like, oh, we can take a Laplace transform, like, oh, we can, there's a pattern, the differentiation one, diff property, where we take something like this, y double dot, I'm just gonna do this, and then we can transform it into the Laplace domain of it to get s squared y of s, right? Remember that stuff? That's what we did in the first half of the assignment. And in the second assignment, the reason why I made that quick video went over state space equations and how to finish the second half of the assignment. How's the assignment going? Easy? Not that bad? Done? All right, good. So there's one little thing, and someone was asking me about this, but when's the assignment due? So remember what you said? You're like, oh, David, you put Saturday, November 15th. Did you mean to say Monday? And I was like, should I just say no, Saturday the 13th? And I was like, let's put it in recording. Where is it? Oh, that's a trick for next time. Oh, someone's in the chat. Isn't the Laplace for y? Yes, okay. So we're gonna do the official definition, the with IC. Okay, before we do that, so we have this double differentiation, right? 1, 2, right? Which we can transform it into s squared y of s minus s y of t is equal to 0 minus, right? That's an IC. Remember that? Oh, thank you. Thank you. IC, right? And then minus dy of t is equal to 0 minus dt, right? ICs. So, okay, that's your like initial conditions if you wanted to pass this class. Hooray, you're done. But if he doesn't give you initial conditions, then let's use the other marker. No, let's use this purple marker. No ICs. Okay, got it? Easy? Everyone's gonna get 100 on that one? And then let's see. Thank you. Okay. And then there's one thing I want to check out. There it is. And I'll grab that too. Yeah, my little dog. Guys like that? All right, so that's what we were covering at. But okay, back to what I was going to present. And let's go. What does this back button do? Oh, what's that? You like that? You like that, Kennedy? Yeah. Midnight? No, because your exam's on that day too. So I say 10 a.m. because then I can start grading at 10 a.m. Do you want me to grade at 12 midnight? I could. No, I'll be grading once you guys start your exam. I'll be like, okay, use the red marker. Remember that? 221? Yes. I can bring those days back. If you hear the room quiet, then that's a good sign or something. But yes, okay. But I'm gonna make a quick change to the assignment because honestly, I'll tell you this: if you're not watching all the content that I produce, then this assignment's like probably one of the easiest ones. Like there's like little effort that I gotta show you. I changed the assignment by a little bit. So based on reviewing the videos, the two past ones, the only things I've changed, and I'll put this in an announcement too. I was gonna make an announcement. Let's show you. The most critical one that I did was this, log of 10. So if you use the log function for your magnitude, you're gonna get natural log, and that's kind of not what we want to look at. To get power, it's 20 log base 10. So how do you get base 10? Log 10. And then you can see stuff making sense. Remember that RC circuit I was doing? Like, actually, no. Remember that? You got 0 dB. If you're not seeing 0 dB at S is equal to 0 or J omega is equal to 0, then something's wrong. That means you're using natural log. So use log 10. So easy. And for this example, I changed the omega frequency. So instead of starting from -10, start from 0 and then add 1 decade. So instead of going from -10 to 10, we're going to go from 0 to 100. So it shouldn't be that bad. Because what I'm asking for this part is we're going to be doing the semi-log x function. So we're going to look at this like an actual Bode plot. So you know how Bode plots work, remember? Let me see if I were to show you a quick Bode plot. Let's use a different marker. I think the red one's going to work. Let's try it. Where for RC, remember this circuit right here? RC circuit, if we wanted to draw the Bode plot for that. Where here's 0 dB. This is bad marker. 0 dB right there. I should have written it up there. We get this straight line right here. Let me just draw that. You see that right there? And then there's a point where we see this like flat line right there. Here's not F3 dB. In terms of this assignment, it's going to be S3 dB because we're in the S domain. So if you wanted F, then just scale everything by S divided by 2 pi. I'm not thinking straight. Okay. S is equal to 2 pi F. And then to get F, you divide. Yes, you divide. Okay. But you should be seeing 0 dB for this RC circuit. So similarly to this assignment, click it. You might not see 0 dB, but you'll see something that looks kind of familiar. Should I just run something for you guys? Yeah. Okay, let's do it. Okay. Because I want to make sure everyone learns and gets hundreds on this assignment. So let's run your assignment. Because someone's probably asking, David, what's going on? Well, if you looked at the code I gave you guys from the videos I posted and just find your transfer function, you should see the following. Let's run that. Is that going to run? Oh, come on, MATLAB. See that? Does that look like something familiar you got in your assignments? So I probably should be asking this, but the reason why I say, okay, determine the transfer function was for you guys to see that, okay, where are the zeros, where are the poles? Hopefully you guys are naturally seeing that, but let's see. Oh, come on, MATLAB. It's chugging really hard. Okay, so I'm gonna do the following. Okay, so here we have our real axis, and here we have an imaginary axis. So here's a real going across like this, and we have imaginary going like this, right? If I were to draw a black line right here or some line, you see that these poles and zeros are on the left side. So you see the 0 right here, right? Where does that come from? It comes from this. And where's the location of that 0? -A. Does that make sense? Is it making sense, or should I? Nah, I'll just show you this other one. Actually, let me show you this one. This one's really cool. Okay. You see these poles right here, right? Right there, right? See that? if you were to flip it on its side like this, where we're looking purely at the imaginary part, so there's something cool about this, but you see this imaginary axis right here? Here we have 0 imaginary value, here I have 5, and here I have 10, right? What's the value right here? Does anyone wonder what that is? Oh, wait, what number pops up? Let's look at it. Not 0.6, 6.9, not that. Nope, come on. Come on, this is a friendly class. See that number? 7, right? Okay, now let me go right here. Close enough. -7, right? Is anyone bothered by that? Does anyone understand what what's that mean? Has anyone seen that number? Is this assignment making a little more sense now? The formula that Dr. Stuber provided is a really nice formula. If you're not understanding this, then something's wrong. See, the formula he gives you right here is like, oh, here's 2a, a squared. So the point of this equation, to explain it to you, here's your 0, right? Where's your 0 located? At -1.5. And then this equation for the resonator, oh, tip for the day, your omega, so if you have it in this format, your poles are located at these omega values, plus or minus. Make sense? And then, let's go back here. Now does it make more sense? If you were to solve for the poles of this, you can get those values, right? Good. And now let's do number 3. Let me run. Yeah, what's up?
So for the number 3 from 0 to 100, are we still incrementing by 0.1 or?
Yeah, 0.1 or 0.01, whichever you like, whichever makes it look cooler.
Okay.
But I will show you what I have. Oh, someone's chat. Do we use? And yep, just hold up. I'm gonna get there. You guys are.
Exercise 11.
Now let me run this. There you go. So, okay, actually, let me get rid of this camera. Let me pin myself first. Pin. Boom. And there we go. Does that look better? Yes. Cool. So here you go. What does that mean? So after using semi-log on this x-axis, right? And you're going from 0, well, something close to 0, up to 100. What's 100? 10 to the second, right? You see this? Does that look cool? Oh wait, what's this peak at? Let's see. It's not letting me. Oh, close to 7. See? So what we're building here is a resonator. And basically, if you wanted to know what a resonator is, okay, I'll show you guys this. Let me show you this. Page 1. And then let me get rid of that. Oh, chat, go away. There you go. So, in other words, wait for my paper. Thank you. So, in other words, you guys are building a resonator. So if you're seeing some Bode plot, and actually let's look at the Bode plot again that we got. There we go. So we have -30, and it goes up to like some -10 dB, and then goes back down. I know what's going on. So here's -30. Does something like this, and then I guess something like that. Then let's just call this one -10. And this right here is 0. Okay. So you're seeing something like this, right? So if this frequency here is, let's say, S or is equal to 7, right? If you were to kick this box, actually, this is S, right? But if we were to convert this into F, right? F is equal to S divided by 2 pi, right? So this would be, well, 7 divided by 2 pi, right? So,
Can't really see.
Sorry. Thank you. Okay, so if you were to kick this type of box, the cool thing about resonators is that if you kick this type of box, put in a delta function here, delta t, right? What you're going to get at the output is something that looks like this. Let's see, t, the time domain. You're going to see something like this, where from, let's say, from this point to this point is equal to f. That's your frequency, resonance, your resonant frequency. That's what it means. So like, you ever see those plots where you're seeing something like, oh, you do a step response from 0 to like VDD, right? But then when you kick your box, like here's some TD, time delay, right? And then you kick your box and you see some overshoot like this. This right here and this right here comes purely from that frequency, resonance frequency. And this is what bothers a lot of controls engineers. So we want to like minimize this using a damping factor. This means it has a poor damping factor, and you learned that more in like 370. Okay, and if you wanted a damping factor of 1, so this would be like, okay, they do like some zeta is less than like 1 or something like that, much less than 1. But if you have a zeta equal to 1, you're gonna get the following step response. So step response. So a step response for the resonator, right? But if you do a step response for RC circuit, you're gonna get the following, where you just get this nice little curve right here. It's really nice. It's really clean. It's a clean response. Okay, so that's what you're gonna be experiencing in your when you build anything real, like an op amp or some cool circuit like this. But for the purpose of this assignment, you see this? That means you have a resonator. You're gonna have a resonating frequency at this peak. Cool? Okay, so the point is, that's what that plot means. And then, oh, you see this phase right here? Because we have a pole right there, we have this resonating peak. Okay, here's your 0, right? And then you're gonna have some weird phase distortion right there, which is kind of bad. Yeah, you get more gain, but then your phase is really bad. So that's the negative of building resonators. So is that making sense? Okay, now the next edit, and I don't want to talk too much about this assignment because I want to get to your guys' quiz. So that's that. Log 10, use semi-log x. And then same thing with the, and everyone knows how to do this one, right? Conv, easy. Just convolve your denominators. Easy, okay. And then the other edit right here is right here, log 10, semi-log x. That's what Ray was saying. Example, exercise 11. Easy. And, oh yeah, from 0 to 100. Okay. All right, let's get to that quiz is right. Okay, so I've catered for you a special little assignment or quiz or exam or whatever you want to call it. Oh, there it is. So I give you guys the following problem. Consider an analog system described by the state equations. I did these, hand drew these little curvy thingies. It took a little while. Where x of t is the system's input signal, and then you get the output. And now let's go over number 1. So one thing I want to make sure is, okay, so we're going to do state spaces, right? And you guys had that general equations from, I think from some of your book problems. But there's one proof I want you to try to hammer. So the proof is, okay, using vector matrix Laplace transform, show this, just prove that. Okay, so remember from back in, I think, chapter 3, where we were doing the state space equations, SS equations, right? Remember that stuff? We were doing, I think it was a big Q T, right? Or something like that, which is equal to A, was this Q? No, it's dot, okay? A Q T plus b x of t, and then we had y of t is equal to c of q of t plus d of x of t. Remember that stuff? So what was the first thing I talked about in today's little lecture? Differentiation. Remember doing derivatives? We can do this rule. So you see how we have like a double dot here? Well, if you have one dot, then just do s squared y of s. So what we're going to do is something similar to that. So here is the time domain, right? Right? So now all we got to do is just go into the Laplace domain. Okay? And to do that, let me just do that, is, you see this right here? Since it's got a one derivative, right? So that means this right here turns into s of q of s. Does that make sense? And then consequently, well, this is a constant, and then that too. And then when you take the Laplace transform of this just gives you q of s, which is equal to a q of s plus b x of s. Is that making sense so far? And then we can do the same thing with this one. So what's the Laplace transform of y of t? Y of s. Perfect, right? Which is equal to c of q of s, right? And then plus d of x of s. That making sense? Cool. Now, see this q right here? You see this q right there? You see that q right there? So one thing I want to show you is, well, we have q's, right? And we kind of don't like how this is right here and this is right here, right? So one thing I'm going to show you is, if you don't remember your matrix multiplication, we want to make this, we want to put this all like terms on one side. Here's a like term, here's another like term, right? So if I were to do this right here, I want to move this, well, let's move this to the other side, right? So s q of s, right? Minus a q of s, right? Is equal to b x of s. Is that making sense? And we want to factor this out. But we're in matrix multiplication, so there's a special property you got to memorize. Well, if we're going to pull this out, can you see that color? I want to use a different color.
I liked it.
Yeah, okay. Yeah, it's pink. Okay. You guys think it's pink? Yeah, I can't see colors. Well, I could, but we want to factor this q of, well, wait, is that the same color? No, that's not. Ugh. Q of s, right? We want to factor this out. So s, right? However, when we factor out this right here is 1 by 1 little guy right there, I guess, right? But this right here is like some m by m matrix right here, right? If we just factor this out, we're going to lose this size right here. So to keep the sizes constant, we have to put this I vector, or the I identity. I forget what it's called officially, where I is equal to 1 identity matrix. There you go. 0, 0, 1, 0, dot 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 0, dot 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 1, dot 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 0, something like that, where it's like m by m or something like that. That makes sense. It's a square. Okay, so we have to put this I. That's what this means. So don't forget that. If you forget that, you'll cry. Minus, since this right here is some m by m matrix already, we don't have to worry about I. Yes?
Is it important which side you put the Q of S on? I feel like Stuber got really angry when we put it on that side, not the other side, because it was already on the right side.
Yeah, I
Why
hate
would that matter?
He
I
got
thought
really angry about it.
it's wasn't it since people are matrices that they're not commutative?
They're not commutative.
And I have a feeling that if we do it that way, he's gonna dock us points.
That's something I would have to review. But point is, we're trying to get stuff done.
that was funny.
All right.
Wouldn't you end up with the same answer, just on the opposite side?
Honestly, I think so. I'm trying to think about it.
But something may be wrong, because like you
You
said.
could divide, it turns out the same number, so it doesn't really matter.
Yeah, we'll figure it out.
Okay, yeah, well, at least you just know.
No, it should be the same because this is some like square, and this is also a square. Then if you multiply two squares, forget it. I ain't dealing with it.
You know what else is because once you start putting in the matrices, you have these 2x1s, these 2x2s, and that's where it gets ugly because if you displace them, you screw up all your math.
Hmm.
You can see that it's done that way, but mathematically it says you have to break.
Yes.
I think okay. So this right here. Okay, I would verify this. Verify this.
No, that's good, so we know what to test.
Okay, this right here, this multiplication right there. Verify that for me. X or something like that. Oh, multiplication. Okay, is someone gonna verify for me that it's either here or maybe this is on the other side. Could it be here?
Yes.
Yeah.
He was asking you. You said,
I
he
was
said,
like, where's
yeah.
my example?
Should be there, yeah.
He was like, is it here?
That's what we did on the board.
He said, is it here? You said, yes. Is it over here? Yes.
This is on this? Is it on this side or on this side?
It's on the right side. Here,
This is already on the
I
right
did
side, we
another
factored
example
it out,
similar
so
to
put
it.
it back on the right side.
I know what he's trying to do. I think I see it, but yeah, whatever. Let's just whatever. Okay. Because point is, what you're gonna do, and I will just do it on another piece of paper because this is getting messy. He's very picky. I will tell you that. I'll tell you that secret right now. He will find one thing to take dock points off. And, but don't worry about it. He's got OCPD too. Okay. Now just writing it officially. Okay. Q of S is equal to BX of S. What you're gonna do now is, okay, I think you might get picky with this. You're gonna multiply both sides by, multiply here. No. Hope he doesn't get picky about that. Is he? S I minus A minus 1. Is he gonna really get picky about this? S I minus A minus 1.
There you go.
Q of S is equal to S I minus A minus 1 B X of S. Making sense? All right, and now back to our little, what do you call it? This right here, Y of S. We're just gonna punch in that solved equation that we had into here to get the following. Let's see. Where Y of S is equal to, let's see, C. That's a funny looking C. Let's just do these curly brackets. Si minus A minus 1 B X of S. Curly bracket. Plus D of X of S. All right? And now the final step. See this X right here? You see this X right there? Get the following. Let's do a square bracket C of Si minus A minus 1 B plus D X of S. Okay? And then if you wanted to, you can, for completeness, H of S, right? To get you that transfer function itself, which is equal to C of Si minus A minus 1 B plus D. There we go. And that's your transfer function. Making sense?
So far.
Good. So is everyone approve this? Is everyone going to approve this on the exam? Is everyone going to get these weird steps? I would probably,
We're gonna do our very best.
okay, that, I don't know. Review. Okay. So that's one part. Now the next part.
The only reason we even know this is because
Using this formula, actually, let's compare it. Does that look like what we got? There we go. See, there you go. See, there you go. Do. Looks the same. Easy, fun. All right. Now, using this formula, determine the impulse response. And what does impulse response mean? There you go. Perfect. Someone got it. All right. Now, page 4. So now, let's solve for the problem. And the problem we're given is the following. And I'm going to write this on another sheet of paper. Good thing I brought a whole bunch of paper. There we go. Throw that there. And then let me just write this right here. Was that page 5? Yep. It's page 5. And let me put this on the side because I have that power. There we go. Boom. Okay. So I give you a big matrix, and I'm going to call it, let's call it Q of T. That's a bad marker. I'm going to throw that away. It's equal to minus 3, 1, minus 2, 0. Here's your A vector of Q of T. And then plus 1, 3, X of T. Okay, and then the second one I gave you guys is Y of T is equal to 1, 0, Q, Q. And the reason why I'm writing it like this is because this is general, where Q T is equal to Q1 of T, Q2 of T. So there's no subscripts. I didn't put subscripts. This is just general. Okay? So, does it bother anyone there's no D? What's D?
0.
Okay? So that means using our little formula, let's just, should I just write the formula again? Yeah, let's do it. Y of S is equal to C of Si minus A minus 1 B plus D X of S. Okay? So now the next thing is start punching in numbers. And now this is painful. Alright, so this is equal to. So let's do C first. I'm going to do this big bracket. So C right here is, well, here's C, and there's no D. That means C we have 1, 0. That's a C vector, right? Matrix, right? And let's use another marker. And then, does it bother anyone if I just do this right now? S, 0, 0, S. Perfect. Minus A. So, minus 3, minus 2, 1, 0. Minus 1. Is that making sense right now? Clear? A vector, and this is Si. Okay? Now the next thing is, I like this marker. Let's put this matrix right here. What's B? Give you guys, oh, I forgot a sign. That's important. 1 minus 3. There you go. And to verify, let's see. Let's punch this in right there. You see, I forgot that minus. There you go. Okay, and that's our problem that we got to solve. And then close that bracket. And then X of S. Okay, and then there's no D. Make sense? All right. So I could show you one thing. If you understood this, then you can technically really cheese this problem.
Enlighten us.
Huh?
Enlighten us.
And then show us all the steps and we're confused.
Like there's an easy way of doing this problem, but I ain't gonna show you because I can see this. When you see this, there's a special property for that. But we're gonna do the problem the way everyone's gonna normally do it, 25 points. So the first thing is there's an identity I give you, and the identity is if you have A, B, C, D minus 1, that's equal to 1 divided by A, D minus B, C or this is D, this is A, minus B, and this is minus C. Okay? So we're going to look at Actually, before we do that, let's evaluate this, okay? So this entire thing is going to equal to 1, 0, right? Then let's do the big square. I like to color code. Let's do s minus minus 3, so that's plus, right? And then we're going to do 0 minus 1, which is just minus 1, right? Then we have 0 minus minus 2, which is a positive 2, okay? And then we have s minus 0, which is just s. Okay? Making sense so far? And then let's bring out the dark marker because I like colorful pictures. Wait, 1 minus 3, and then close this, and that's x of s. Okay? And now, what I'm going to try and show you guys, and you can actually solve this problem kind of quickly, but not really, is let's evaluate, let's not use this marker. Let's evaluate this first, and we're going to look at the poles. So one thing I'm going to try and show you is we're going to use this equation right here, and we're just going to solve for the poles, or I'll show you what I mean. So rewriting this entire thing so we can get this middle thing, we're going to get 1, 0, right? And then for this little equation, we have 1 divided by AD. So here's A, here's D, right? So we're going to get S times S and then 3 times S. So I'm going to do this 1 minus, or 1 divided by S squared, right? Plus 3 of S, okay? And now we got to do minus B times C. So here you have B, and here you have C, right? 2 times minus 1 is minus 2, right? But then minus 2 times minus 1 gives us positive 2. Okay? And then all we got to do is just flip this matrix. So we got S, and then S plus 3. And we have, flip the sign of this, so it's positive 1. And then flip the sign of this, so it's minus 2. Okay? And then, oh, should be color coding this. This is a 1, it's 3. And then close that bracket, x of s. What? Oh, thank you. Okay, so there's one thing I want to show you. See this right here? Can you find me the roots or the poles of this? Yep, let's look at this. Where this right here is equal to s plus 1, s plus 2. Yeah, the reason why I picked these poles were, well, we're not in the other room. In the other room, I actually have the answer, but because I like 1 and I like 2. Those are easy. You saw that? The benefits of coming to class, right? And then what does this tell you about the system? It's stable. And it's causal, assuming that it's, well, right-sided. And, well, it is. It's always right-sided. Okay? It's a stable system because all the poles are on the left-hand side, or left-handed, or all poles on left hand, or left side, left-hand sided. Left-sided poles, you know what I mean, right? It's stable.
Stable and causal.
Are we just to assume that, or
Stable?
and causal?
Well,
That's how it's explicitly stated, or can they assume?
that's a good question. I'll look at that. Don't worry. If he says stable, then you have to make sure it's stable. So I'll show you later. But first, let's finish this, okay? That's a good question. You brought up a really good question, and he might actually trick you. And I know exactly what you're talking about, or what you're trying to get to. 6. Okay, so rewriting everything. Does it bother anyone if I do this, where I pull the transfer function out? I'm gonna call this s plus 1, s plus 2, Does that bother anyone? Good. Then, oh, I wrote it on the marker. Oh, you didn't see that? 1, 0. Then let's rewrite that matrix. S1 minus 2, S plus 3. Good. And then 1 minus 3. Okay, making sense now? So there's two ways of approaching this. You can either go with, okay, here's 2 times, here's a 2 by 2 square, right? Here's a 2 by 1, right? You can either do this to get 2 by 1 square, right? Or rectangle, right? Or, you see the 0 right there? So this is a 1 by 2, right? That 0 is going to cancel a lot of stuff out. And you like, in this problem, zeros are good. So instead of doing this, why don't we just do this? Okay? To get us 1 by 2. Okay? So I'm going to do this. Okay? So rewriting this, I'm going to call this one H poles. Is anyone bothered if I do this? Nope. Good. So now, oh, what's his name? Doing this, we're going to multiply this times this. Well, multiply this and add it to this and this. But you see it's S plus 0. It just gives you S, right? And then we're going to do it right here. We got 1 times 1 times this, and that goes away. See? And you get 1.
Can you write the property down, maybe?
Property?
To do the math and the inside matrices.
Didn't,
How you would do that?
didn't everyone learn this in Matrix?
Oh,
Remember, we never had this
yeah, no,
conversation.
I took that class. They didn't take that class.
Oh.
It's not. If you want to become a doctor, you have to take it. That's why I took it.
Assume at this point forward that we're not allowed to say matrix math or linear algebra.
It's just columns by rows, and then in order for you to multiply 2, they have the insides have
Okay, you know, I'm just going to do this work.
2 and 2 have to be.
Sometimes it's best that way, David. We're not very smart.
S times 1. Okay? Plus. So I'm okay. I'm getting really OCP about this. 1. I'm going to look at this. And then, where's the other marker? We're going to look at this. Okay? S times 1, all right? Plus. Then I'm going to pull out 1. Okay. S plus 1. Then minus 2. So I'm going down this way right there, right? Minus 2 times a 0. Oh, wrong marker. Come on, 0. Good? Okay, and our overall result is going to be a 1 by 2, okay? That's 1. Now we're going to look at row 1, column 2. Okay? So that means the next part is, let's use the purple marker. Okay? So now we're going to move to this one. Okay? We're going to do this. So here we have 1, actually, 1, that's this green. And I'm going to look at this right here. Okay? 1 times 1 plus, here's a 0, 0, okay, times this. And let's use the purple marker, S plus 3. Okay, but you see how this goes away? And then this goes away to give you the following result. H poles S of, hold up, of S1. There we go. Oof. Does that make sense? Is that clear?
Yes.
Okay, perfect. Oof.
Sorry. He's like, no, do it again.
I have to go. I'm trying to figure out how slow to go. All right, and then back to our nice marker. 1 minus 3.
Too fast.
Okay, good. Which is 2 by 1 matrix. So that means what's our result? If we do this, we're going to get a 1 by 1, okay? So that means, okay, because someone's probably getting really confused or enlightened or wants me to try to click time. Oh God, 6 minutes left. I can't believe it. We got a lot more to go over.
That's why
That's why we're here.
Okay, so we're gonna look at this and this. Okay, we're gonna multiply s times 1. S times 1, okay? Then we're gonna look at this and this. 1 times minus 3. This is plus 1 minus 3, okay? To give us poles of s, s minus 3. Is that clear? And now you see where h poles of s is?
Chat.
Oh, chat, thank you. X of s. Oh, thank you, OCPDs. Thank you. I'm playing with y'all. I have it.
No, that's very important.
That is actually very important.
That's very important.
Because, actually, you're right.
Sons make the brick.
And then x of s, because this entire thing right here is h of s. Okay? And that means y of s is equal to, well, h of poles is that. You're going to get s minus 3, s plus 1, s plus 2, x of s.
Oh.
Okay? And now, what is the impulse response? Huh?
Is that still the answer?
Hold up. So, impulse. Okay? So, you remember this little delta function, right? What is the Laplace transform of this? So that means if you have y of s is equal to h of s and x of s, where x of s is equal to that, right? X of s is equal to Laplace transform of delta t, right? That means your impulse response is literally just h of s. Well, in the s domain, which means your real answer is, well, s minus 3, s plus 1, s plus 2. Okay? And now the next thing is, okay, how do we see this in the time domain? And that's a good question. Actually, before we even go to the time domain, that too, but where's the poles and zeros of this? So we have a 0 right here, right? This 0 is located at, when's the top go to 0? 3. Let's write that right here. 3. And we're going to draw a circle. Or should I make that in red or green? No, let's make it cool. Or green. I'm using green. I'm going to use red for the poles. Then we have a pole, right? Where do we have our poles? Okay? And because we want a stable system, right? Here's the imaginary axis, right? So that means, how do we make this stable? We look at the farthest pole like this, and that's your region of convergence. ROC. Okay?
Stable, 'cause you said it's stable, or?
It's stable because our region of a convergence includes this imaginary axis. It's in.
Are we gonna be drawing on this test too?
Nope.
Oh, okay.
Mm-hmm.
If there are no poles, then the ROC is all of us.
Huh?
If there are no poles in the function, is our ROC all of us?
Yes, all of it.
Everybody.
Stable since ROC includes J omega. Okay,
Imaginary axis, okay.
that's what it means. Okay.
No, you don't have to write it. I was just saying that.
Okay, easy. So that means, actually, now I'll go over that later. Okay, now let's solve for h of t. Or before h of t, see this? Partial fraction expansion. So I'm going to do the following, and I'm lazy. S plus 1. Does that make sense?
How's that easy?
I'm just writing it down here. Okay, I'm gonna just solve for A and solve for B, where A, using the, I think, is it called heavy side?
Yeah, it is.
Okay. Yeah, I think so. I don't remember. All right. Where we're gonna analyze. Okay, where does this a term like go to infinity when s is equal to -1, right? Okay, so we're gonna have to analyze this without the pole at s is equal to -1. So that means rewriting this, okay, s minus 3, s plus 2, where we evaluate this entire thing at s is equal to -1. So that means here's -1 minus 3, -1 plus 2. What's that equal to? -4 divided by 1. -4, right? Okay. And now let's do b. And where does b go into infinity? When s is equal to -2. Okay? That means s minus 3 divided by s plus 1. Okay? We're following? Is equal to -2 minus 3 divided by -2 plus 1. It's equal to -5 divided by -1. Positive 5. Make sense? Which means our final answer okay? And now, remember the thing I was trying to tell you about? Well, this right here is a residue. And this right here is a pole. And that all general equations, let me see if I can do that on the side. Gen equation is y of t is equal to res e to the pole of t. Remember that? And let me put this in parentheses. Okay? So, rewriting this in the time domain, what do we get? 4 of e to the minus t plus 5 e to the minus 2t. And do not forget this, please. There we go. And I'm going to do this in a red marker. Forget that, you're going to be sad.
Forget what?
U of t.
Yeah, them brackets, them goddamn brackets.
Brackets?
Brackets.
It could be in parentheses or whatever triggers your OCPD.
So that was just the inverse Laplace.
Yes, the inverse Laplace transform of this entire thing. But should I use your assignment to solve something crazy?
Yes.
Okay. Let's see. So let's pull out an assignment. Okay. Oh, remember exercise 9? Let's look at this. Oh wait, not that one.
Yes, let's look at that.
So you can actually verify this in MATLAB. So in the second half of the assignment, you're using state space blocks. You're trying to draw and label a direct form 2 block, and then you can solve for the hand calcs of this, easy peasy, and you can use MATLAB to solve for verify your hand calcs of exercise 9. Okay, simple. So what I'm going to try and show everyone is, so what is the transfer function of our state space equations? So what I'm going to try and do, and let me see if I can put this on another piece of paper. Okay, let's copy that right there. Boom. So this right here is our block diagram that I got. Okay, that's our quiz. Okay, this is quiz. Let's call this one lecture. Okay. Oh, nope. Lecture 14 or 13. Yeah, 14. And now what we need to do is, let me show you this. We need to transform this into, let's see, what's the equation I use? Let me remember something. Give me a moment. Oh, that's a lot of calculations. What did I do? Okay. So there's a function, and I'm going to try and show everyone this. Actually, let me bring up the other paper. So there's a function right here, and it's called state space to transfer function. So you already have your state spaces, right? That's our quiz right there, right? So you're like, well, gee, what's a transfer function of our state space equations? Oh, there's a function for that. SS to TF. And if you enter that, enter. Oh, run section. Okay, we just inputted our variables. Here's our quiz right there, right? And now calling our equation. What's that look like? Let me write that down, and this is page 7. This is page 8. And MATLAB is saying, okay, MATLAB is saying our numerators are at, okay, h of s is equal to, okay, so it's going to do it in the following. It's going to do 0s squared plus 1s minus 3, okay, divided by 1s squared plus 3s plus 2. So rewriting that, it's going to be s minus 3 divided by s squared plus 3s plus 2. Oh. And that's MATLAB's version. Did we do everything right? You verified it. Congratulations. We did the quiz correctly. Okay? So that's how you can use MATLAB to solve for all this stuff, okay? So now, is everyone going to get 100 specifically on this problem?
On that problem, I'm going to say at least a 22.
Wait, why does the top go just to s minus 3
S minus 3?
from that equation?
That becomes
Oh.
0.
And then 1s.
So why is the bottom 1s and the top is 0s? Okay, never mind.
No, because of
I
we're,
was like,
we're,
wait, what?
we are reading MATLAB. See this
Oh,
right
okay,
here? I call it the numerator right here. It's okay. SS to TF is asking for numerators and denominators. Boom.
I see it now. At first I was like, why'd you put that 0 there?
All right. So then
It's what it spit out. Got you.
let's see. There's one last thing I want to show everyone. Everyone's gonna ace this state space equation stuff, right?
Yeah.
And remember that quiz that we did last week on the RC circuit stuff? Everyone's going to get that convolution or that stuff we were doing last week? Okay, where we had that initial condition.
That one is in progress.
Okay, so before I go over, so suppose, and I'm going to go back to your question because that's really important. So suppose he gives you a stable system.
I forgot the question.
Okay, so a stable system is basically where we have, okay, let's call ROC includes imaginary axis. Okay, remember that? So what happens if I draw you this, okay? Right? L of S, okay, right? What happens if I do, let's choose, let me see, what are my poles? Should I? I'm trying to figure out what poles I want to give you. Let's give you this. Okay, let's call this one -1 and let's call this one 2. Okay? So how do we make this system stable? So okay, if we were looking at this, let's color this one red, right? If we were just looking at one pole, then the region of convergence is going to be like this, right? But for this system, let's color this one black, okay? Right? How do we make this pole stable? You got to include this. Okay? But how do we get a stable system? we had to color this region to include this. And that's how we, so that means, what does this tell you? That means this pole right here, I'm going to call this one, it's going to be right-sided. Okay? So that means what you're going to do is, if you had the following, let's give it a residue value of, should we give it a residue value of, what number you guys like? 3. Okay? This one has a residue value of 3, okay? So in the Laplace domain, L of S, okay? If you're going to get 3 divided by S plus 1, right? And then you see this pole right here, right? This right here is going to be a, let's color it black, left-sided, right? So what number do you guys like? 12.
Yes, that's correct.
Okay, so that means plus 12s minus 2. Okay, so this is left-sided, and this right here, and yes, I got to do color codes because I like colors. Right-sided, right? So if you're trying to do the inverse Laplace transform, let's call it L of t or something like that. Just giving it a random number. If you were going back into the Laplace domain, you're going to get 3e to the minus t, right? And if we go to infinity, right, it's a right-sided. Okay, let me draw this. Hold up, before I do that, right? We're going to infinity, right? Here's t, right? We're going to infinity, right? So that means we have to stop right here, right? So you got to put a u of t right there, right? To make it a right-sided function, okay? But for this one, this is a left-sided function. So what we have to do for this one is you have to change the sign. I think so. I think you have to change the sign. So it's 12e to the 2t u of minus t. Here we go. So that means this becomes left-sided. So that means this is going to look like, this is a function of t, minus 12, I think so. It's like that, something like that. I'm just picking random numbers. This is just fake.
So,
Okay.
are we saying there that if we solved out our whole H of S, and we got that and that, I could say that because that one's at a minus, it's left-sided?
Because this right here is a
That
left,
way, that's how I make my determination.
No,
I can't do that?
or no.
you're saying that it was stable, it had to be left-sided.
Yep.
That was if you had it, it's stable.
See how this pole right here is on this side right here? That means if it's on the right side of the imaginary axis, it's going to be, it's not causal. This is actually non-causal. Because we have something on the, something before t is equal to 0. It's a non-causal system. So this right here is a stable system, but it's not causal. If you want a causal and stable system, well, this is not, well, you can't have a causal system because you have something before time. All right? So right here, we have a left-sided pole, right? We have a pole on the left side, right, of the imaginary axis. It's right here. Okay? To make it stable, we have to go to the right. But since it's also going to the right, it's also causal. So that means you just do this natural number stuff. This right here is on, this pole is on the right side of the imaginary axis, right? If you try to make it a right-sided function, so keep this positive, it's going to blow up. It's not stable. So how to make it stable? You have to make it left-sided. So it's left-sided here. So it's non-causal, but it's still stable. So take t to infinity. Does this blow up? No, because you have this minus t. There you go. Don't forget. Okay, let me write that down. Okay? But, okay, one last thing. What if I added the following? Plus 2 to the entire transfer function itself. Okay? Actually, okay, let me write this on another piece of paper. Last thing. Page 9. So rewriting that Laplace transform let's call it h of s, whatever, is equal to 3s plus 1 plus 12s minus 2, right? If you can draw that, you can, okay, here's minus 2 right here. Wait, plus 2, right? And then this right here is a left-sided pole, so here it is minus 1 right there, right? So to make it stable, okay, rewriting it again, this needs to be a right-sided equation right here, right? And then this right here, to make this one stable, this one needs to be left-sided. So this right there and that right there. But what happens if I do this? Add a 2 right there from partial fraction expansion. How do you write that in the time domain? Yep. So if I were to go to h of t, you're going to get 3e to the minus t, okay? U of t, right-sided, okay? Minus 12e to the minus plus 2t, okay? U of minus t, which is left-sided. Then plus 2 delta t. And does that make sense?
Yeah.
So he's going to give you some like first or second. Well, why does this pop up? Why does this pop up? What does a delta function mean practically? Does anyone know what that means? So if I were to give you the following thing, like some gain block, so like maybe some b0, right? X of t, right? Y of t, right? And if I make this equal to the delta function, right? And b naught is equal to 2, what's y of t? What does that mean? That means you have a direct path from input to output. So what does that? That means there's no circuits between the input and the output. You just have a gain circuit. It just flies through the circuit at time is equal to 0. Is that really cool? It physically means nothing. Physically means nothing.
This question physically means nothing.
But we can use it for mathematics. Okay? Because what happens if this delta function right here, right? Let's finish this problem up. It's almost 6:50. What happens if we connect this output to some integrator? Then that's where if you integrate the delta function, you get that, like you get a constant u to u of t. Ah, isn't that cool? Well, if you put some constant dc into an integrator, you cause instability, but don't worry about that. But point is, it physically means nothing, so you don't simulate. If you wanted to prove this in MATLAB, simulate this. Sim. And then don't sim. Don't sim. Because that's just, it's so tiny, it's infinity amplitude long, it doesn't mean much. So you just really simulate this. Any other questions? And I think I've covered everything that I kind of wanted to. RC circuits, Laplace domains, ICs. If he gives you an IC, you already know what to do with that. Shouldn't be that bad. From the RC circuit, should be okay. All right. Any other questions? Chat, we're doing good? All right, have a nice day.